When we look up at the sky on a clear night, we can see several thousand stars. All these stars are part of the galaxy in which we live. We know that our galaxy is not the only one. There are thousands, millions, billions of galaxies in the universe. We can see them, at a great distance, shining through our own galaxy's starry curtain. But why are there galaxies at all? This question still cannot be answered conclusively, but by observing the oldest and most distant galaxies, astronomers have discovered that they were formed shortly after the birth of the universe. This means that our galaxy is probably nearly as old as the universe, about 13.6 billion years. Thanks to new technologies, it is possible to look deeper and more precisely into space than it was 100 years ago, in the days of Edwin Hubble, who proved that our Milky Way system is just one galaxy among millions and millions. And it has been discovered that there are more galaxies in the universe than stars in our Milky Way. Scientists want to find out more about the galaxies. What are the differences between them? How did these differences come about, and why do they occur? This is what we want to talk about in this video, and the next videos in this series. Let's start with the galaxy we live in, the Milky Way galaxy. If you look at the stars in a particularly dark night sky, a faint band of light can be seen stretching across the firmament. The Greeks observed this shining band more than 2,000 years ago. They called it galaxias, the Milky Way. This name goes back to a legend from Greek mythology, brought to canvas by Tintoretto in 1575. It tells how Zeus, the father of the gods, tricked his wife, Hera, into breastfeeding little Heracles, so that the baby could drink the milk of the gods. When Hera realized this deception, she became angry and threw the baby away. In doing so, she splashed her mother's milk all over the sky. So, the Milky Way was created. As early as 400 BC, the Greek scholar Democritus suspected that the Milky Way is actually made up of many faint stars. However, no one was able to observe this at the time, as there were no telescopes. It was not until 1610 that Galileo Galilei was able to prove with the help of his self-built telescope that the shimmering pale nebula of the Milky Way consists of countless stars. He wrote down his observations. My third observation concerns the nature of the Milky Way. No matter which of its parts the telescope is pointed at, an enormous number of stars will immediately appear, some of which are quite large and very conspicuous. The number of small stars, on the other hand, is absolutely unmanageable. The English scholar Thomas Wright made the first scientific attempt to explain our galaxy in 1750. He already held the view that we live in a disc-shaped accumulation of stars that slowly spin around a center of mass. 5 years later, the German philosopher Immanuel Kant also proposed that the stars of the Milky Way form an extended flat disk, shaped by gravity, which Isaac Newton had discovered a few years earlier. Wright and Kant concluded independently of each other, our solar system is located within this disk. When we look at the plane of the disk, we can see the light of countless stars drawing the band of the Milky Way in the sky. The first real investigations into the structure of the galaxy were based on counting stars. Even stars counted with the naked eye show an asymmetrical distribution. In 1785, William Herschel, probably the most diligent observer of his time, arrived at an initial idea of the disk shape of the Milky Way system, assuming that the Sun and our planetary system were located fairly exactly in the center. However, on this point, Herschel was wrong. His method could not lead to a realistic view because Herschel did not take into account an effect, whose significance was not fully understood until the 20th century. Namely the fact that the light of distant stars is strongly attenuated by interstellar dust clouds. Much later, the Dutch astronomer Jacobus Kapteyn even catalogued almost 500,000 stars. This enabled him to develop the first spiral model of the galaxy around 1900. In 1922, Kapteyn published his life's work, in which he introduced the model of a disk-shaped rotating galaxy with a diameter of 40,000 light-years and the Sun being relatively close to its center. This approach is similar in some ways to our current understanding of the galaxy, but still contains many errors due to the lack of knowledge at the time. By studying the distribution of the so-called globular clusters, Harlow Shapley arrived at more realistic estimates of the size of the Milky Way in 1919. Globular clusters are huge star clusters surrounding the galaxy and taking up an almost spherical space around the Milky Way within the galactic halo. Shapley found that these clusters were significantly more numerous in one direction, namely towards the constellation of Sagittarius, than in the opposite direction. From this, he concluded that the galaxy's center of mass must be located in Sagittarius, and that the Sun is not at the core of the galaxy, as previously assumed, but at its periphery. Shapley was right about this, although he was fundamentally wrong in other aspects, and more than once. For example, by estimating the diameter of the Milky Way to be 3 times larger than it actually is. He also firmly believed that our universe consisted exclusively of our own galaxy. Shapley considered the other galaxies, which had been observed in large numbers until then, to be objects within our own Milky Way. Today we know much more about our galaxy. But how did this knowledge come about? At first glance, the Milky Way is just a faint band of stars. Some bright, but most of them very dim. The Sun is obviously just one of many stars in a large disk. Closer inspection reveals that the disk is more densely populated with stars in one direction, where it is also thicker. As Shapley did, one could assume that the center of gravity of the disk is located in this direction. We can see this in the many other galaxies, such as the Andromeda galaxy, which is probably very similar to our own. Or any galaxy that we look at from the top, such as M77. Our Milky Way appears the same from above. Since we are in the interior of this disk, it is very difficult to determine the true structure of the galaxy using only visual or statistical clues. You could analogize this to the task of describing the size and shape of a forest when you are in the middle of it. Of course, it would be best to look at the forest from a bird's eye view. Only then it would be possible to grasp its full extent. But from a position in the middle of the forest, between the trees, this task is difficult at best, if not impossible. A further problem is that we can only look a few thousand light years from our position out in the galactic plane. Beyond that, interstellar dust masses and a curtain of dense stars block the view of more distant regions, at least in the visible spectral range. But how did the scientists manage to obtain a realistic model of the galactic structure, despite the many unfavorable preconditions? They achieved this through decades of observations and studies, such as the mass distribution in the galaxy, the rotation and kinematics of stars and other objects, as well as research into the various objects and components of the galaxy, such as stars, clusters, satellite galaxies, stellar streams, and associations. We will discuss many of these details later, and in the second part of the video series. All in all, the study of our galaxy is an enormous task that has been going on for about a century, and is still far from over. The Hipparcos astrometry satellite, launched over 30 years ago, had already precisely measured the positions of over 1 million stars, which has led to many new insights into our galaxy. This task was continued by the European Gaia Space Telescope, which measures the galaxy in 3D. In 2016, a first map of the galaxy was created, based on the astrometric data of more than 1 billion stars, meaning their positions, distances, directions of movement, velocities, and much more. 2 years later, the most detailed map of the Milky Way to date was published, derived from the countless data collected by Gaia in less than 2 years. The accompanying second catalog contains almost 2 billion stars and many other objects in our galaxy. Now let's take a look at what our home galaxy is made of. The majority of stars in the galaxy are distributed almost evenly across the galactic disk. The dense central region, known as the bulge, stands out clearly from the rest of the galaxy. For one thing, it appears much denser, and for another, it generally bulges far beyond the plane of the disk. In fact, this is the geometric and mass center of the galaxy. In many older publications, the diameter of the galactic disk is given as around 100,000 light-years. According to more recent studies, it is likely to be somewhat smaller, and a diameter of around 85,000 light-years seems more realistic. The disk and the bulge are surrounded by a spherical halo with a radius of more than 80,000 light-years. It contains the already mentioned globular clusters and other stars, which are among the oldest in our galaxy, as well as hot gas. In addition, the existence of invisible dark matter is suspected in the halo and perhaps far beyond. In the galactic plane, stars have been discovered at a distance of about 90,000 light-years from the core. Some authors therefore believe that a much larger diameter should be assumed for the Milky Way galaxy, at least 170,000 light-years, since there is most likely still a very thin galactic disk with individual stars at this distance from the center. There are very different estimates for the visible mass of our galaxy. It is generally assumed to contain between 100 and 400 billion stars. Our Milky Way can therefore be counted among the larger spiral galaxies. Nevertheless, it is significantly smaller than its neighboring galaxy M31, the Andromeda Galaxy, which is about twice as large and at least twice as massive. In any case, when determining mass, only the visible or measurable matter is taken into account. But the mass of our Milky Way galaxy is probably much higher, possibly between 950 billion and 1 trillion solar masses. This assumption is based on the research of astronomer Ekta Patel and her team. They analyzed the orbital movements of known satellite galaxies. These are smaller companion galaxies orbiting the Milky Way on elliptical paths. They move in bound orbits within the gravitational potential of our galaxy. The measurement methods used by Patel and her colleagues are basically comparable to those used to calculate the Sun's mass when studying the parameters of the orbiting planets. The crucial difference, however, is that Patel and her team focused on the angular momentum of the satellite galaxies. The angular momentum depends on the mass and distance of the respective galaxy and always remains constant during the orbit, which means that it is not subject to fluctuations like the orbital velocity. Until the 1990s, it was assumed that the Milky Way was a fairly uniform spiral, similar to the Andromeda Galaxy. As a matter of fact, research has shown that our galaxy is actually a two-armed barred spiral galaxy. Due to the motion of interstellar gas and the distribution of stars in the bulge, the galactic central region appears to have an elongated shape. According to observations by the Spitzer Infrared Space Telescope, the bar-shaped central structure is surprisingly long, with an extension of about 27,000 light-years. At first glance, our galaxy appears to be a flat disk. But this is deceptive. According to recent observations, the galaxy is clearly distorted. Its main plane is warped, one side is slightly bent upwards, the other downwards. The origin of this deformation is still unclear. Assumptions range from the influence of dark matter in the galactic halo to the effects of interactions or mergers with other galaxies. This phenomenon is not unique to our galaxy. Similar deformations were found in about half of all known spiral galaxies in the universe. The visible spiral arms are mainly dominated by hot and brightly shining stars, but also by star clusters and luminous gas nebulae. At least it is these bright objects which illuminate the galaxy. However, the brightest stars are actually quite outnumbered. The largest group of stars by far are much too faint to be visible at greater distances. The so-called red dwarfs. Their enormous number also makes a major contribution to the mass of our galaxy. Our solar system is located in a fragment of a spiral arm, called the local arm, around 26,000 light-years away from the galactic center. It takes the Sun an average of 230 million years to complete one orbit around the center of the galaxy, a so-called galactic year. This corresponds to an orbital speed of around 220 kilometers per second. Recent measurements have even shown a higher orbital velocity, about 270 kilometers per second, or 961,000 kilometers per hour. However, as already mentioned in the video about the supposedly fast-moving Earth, which in reality takes 7 minutes to cover its own diameter, the speed of the Sun must also be put into context here. Our Sun's diameter is about 1.4 million kilometers. If you divide 1.4 billion by 961,000, you get a factor of 1.45. In other words, the Sun takes about 1 hour and a half to cover a distance equal to its own diameter. Now take a ball and roll it so slowly that it takes 1.5 hours to cover its own diameter. It will seem to you very, very slow. Nevertheless, this motion is actually too fast. According to calculation, it would be expected to be around 160 kilometers per second. However, we detect a speed that is almost 60% higher. This means that there has to be much more mass near the orbit of the Sun than would be expected according to the calculations. About twice as much. The significantly too high orbital speed of the solar system around the galactic center is therefore a further indication of the existence of invisible dark matter. As early as 1932, Jan Hendrik Oort suspected the existence of invisible matter in the disk of the Milky Way, based on his investigations into the number, density, and distribution of stars. It was not until the 1970s that Vera Rubin discovered, not in our Milky Way, but in a neighboring galaxy, that the rotational speed of the stars did not behave as it should from the calculations. From this, she also deduced the existence of an invisible mass. The solar system therefore does not orbit the galactic center on an undisturbed flat Keplerian orbit. The mass distributed in the galaxy's disk exerts such a strong disturbance that the Sun regularly swings up and down through the disk, in addition to its orbit around the core. The Sun crosses the galactic plane approximately every 30 to 45 million years. About 1.5 million years ago, the solar system crossed the plane in a northerly direction and is now about 60 light-years above the galactic plane. The galaxy's spiral structure was only suspected for a long time. It has been observed that many other galaxies have spiral arms. This was confirmed by observing the distribution of neutral hydrogen gas in the Milky Way. However, the spiral arms, like those of all other spiral galaxies, remain an unsolved mystery. Due to the rotation of the galaxy, the spiral structure should have dissolved after just a few revolutions. Instead, however, the spiral structure of a galaxy apparently remains intact for many billions of years. It seems clear that the spiral structure is somehow related to the galaxy's rotation. To a certain extent, it is possible to simulate the formation of a spiral shape with computers. In doing so, a certain similarity with the behavior of sound waves in a rotating medium can be observed, since acoustic waves also propagate in a spiral or helix shape inside a thin rotating disk of specific size. One theory describes the spiral arms as a wave phenomenon. According to this, the spiral arms constantly rearrange themselves. As early as 1925, the Swedish astronomer, Bertil Lindblad, put forward a theory, according to which the orbits of the stars inside galaxies resonate with each other. As a result, they synchronize, and so-called density waves are formed. This led two scientists, Chao Lin and Frank Xu, to develop the so-called density wave theory in the mid-1960s. In simplified terms, density waves are supposed to run through the galaxy, with the spiral arms representing the most dense areas. The interstellar matter is compressed by these waves to such an extent that new stars form in these areas. The rotation of the density wave is decoupled from the star's orbits. In fact, the density wave rotates significantly slower than the stars. In our Milky Way system, the density wave is rotating at a speed of around 13.5 kilometers per second per kiloparsec, corresponding to half the orbiting speed of the stars. The visible spiral arms are formed after the gas flows into the density wave, and is then compressed. Regions with an already high gas density, such as molecular clouds, become unstable and start to collapse, creating new star clusters and starburst regions that become visible behind the density wave. A density wave could be compared to a traffic jam behind an obstacle on the highway. Cars pull into the traffic jam, the traffic density increases, and after the obstacle, the cars pull out again. The obstacle also moves forward, but slower than the cars and at a constant speed. According to this hypothesis, the different manifestations of spiral galaxies, such as unbarred and barred spirals, would merely be different appearances of a density wave. Our galaxy would therefore also go through these different stages. Stars and gas clouds move in and out of such a compression area several times on their orbit around the galaxy. In the process, gas is condensed and new stars are formed. The most massive, and therefore very short-lived among them, shine bright and thus characterize the appearance of the spiral arms. Due to their short lifespan, they never leave the spiral arm, but explode beforehand as supernovae, and boost further star formation, due to the resulting shock waves. It may look as if the stars only exist in the spiral arms, but there are also quite a large number of stars between the arms. This hypothesis has some weaknesses. For instance, it is still completely unclear as to what causes these density waves. They could, for example, be triggered or boosted by gravitational interaction with other galaxies. As we will learn in the next video, our Milky Way is actually an interacting galaxy. Many smaller and larger galaxies have left their mark on our galaxy in the past through their gravitational effects. So the density wave model is far from being able to answer all questions about the spiral structure. For example, it is not yet clear what role the galaxy's magnetic fields play in the spiral structure. Magnetic fields are an important component in spiral galaxies. Every galaxy has a distinct magnetic field, but their origin is not yet clear. According to one hypothesis, they are generated by the motion of electrically charged matter. Progress in observation technology has not only brought new insights, but also raised many new questions. One of the most important unanswered questions concerning the rotation of the galaxy is the fact that all stars outside the central bulge move around the core at approximately the same speed. This was discovered back in the 1960s when it became possible to measure the rotation curves of spiral galaxies. The aim was to clarify the question of how fast a star orbits around the central region at a specific distance. The expectation was that the orbital velocity would initially increase rapidly near the center and then slow down in the spiral arms, similar to Kepler's laws in the planetary system. However, Vera Rubin and Kent Ford discovered that the speeds hardly decreased with increasing distance from the core of the galaxy, apart from slight fluctuations. Although the density of observable matter drops significantly with greater distance from the center. This was surprising, as a drop in velocity outwards was expected if only the gravitational effect of the visible matter was influencing the motion. For science, this is the most important indication that all galaxies, including our very own, are embedded in a halo of dark matter that strongly influences the rotation of the disk. Dark matter means that apart from its gravitational pull, it has no further interaction with the visible matter we know. It must also be located between the stars and the quantifiable interstellar matter, which only makes up around 15% of the galaxy's mass. According to the theory, the measurable proportion of matter, consisting of stars, gas and dust, is, so to speak, only the tip of a largely invisible cosmic iceberg. This hypothesis also partly explains why the spiral structure of a galaxy remains intact for billions of years. If the matter in a galaxy would rotate according to Kepler's laws, the spiral structure should have dissolved or unwound after just a few revolutions of the galaxy. The only way to explain all these phenomena is to assume that there are large quantities of additional but unmeasurable dark matter inside the galactic halo. The spherical galactic halo, which surrounds our galaxy like a huge bubble, probably has a diameter of more than 150,000 light-years. It could be described as a sort of galactic atmosphere. In addition to the approximately 150 known globular clusters, it contains scattered old stars and hot gas at very low density. This gas can only be detected in X-rays. It has been shown that the halo is not at rest, but rotates at a similar speed to the galactic disk and in the same direction. By measuring ionized oxygen from bright X-ray sources in the halo, it was possible to determine an average rotational speed of the gas of around 180 kilometers per second. The scattered stars inside the halo are mostly found in so-called stellar streams, the result of interactions with globular clusters and other galaxies, from which they were torn out by the gravitational pull of our Milky Way. In contrast to the galactic disk, the halo is largely dust-free, but contains this hot gas, whose origin we will also discuss in the next part. Globular clusters are spherical agglomerations of several 100,000 to millions of stars bound together by gravity. Their entire number is estimated at around 200 to 300. They are tied to the galaxy, in whose halo they move over a large area. They orbit around the galactic center and occasionally cross the galactic plane. These clusters consist mainly of old red stars of the so-called population II, containing only a few heavy elements. They are therefore strongly reminiscent of small galactic nuclei. Astronomers refer to certain subgroups of stars that have similar properties as a population. The stars existing in the different areas of a galaxy, that is, in the disk, the bulge and the halo, also differ in their age and chemical composition. Astronomers have therefore developed various classification systems to categorize stars, according to their distribution in space, their motion, their age and their composition. The question is therefore whether these stars occur in the same region of our galaxy, and whether they consist more of lighter or heavier elements. This is the so-called metallicity. As we have already learned in our video series about life in space, astronomers, unlike chemists, refer to all elements that follow hydrogen and helium in the periodic table as metals. For astronomers, therefore, not only gold and iron are metals, but also oxygen and carbon. More rarely, all elements from carbon upwards, that is, from a nuclear charge number of 6, are considered metals. Astrophysicists therefore often refer to the chemical composition of stars as metallicity or metal abundance. This classification of stars according to their location and metallicity is called stellar population. According to an older definition, there are two main stellar populations. Population 1 contains a large proportion of interstellar matter, and the brightest population 1 stars are very hot and glow white or bluish. They are mainly located in the galactic disk. This is the largest group of relatively young and stably luminous stars that move in almost circular orbits around the galactic center, mostly in the spiral arms. They contain a quite high amount of heavy elements, which were formed in earlier generations of stars and cause metal lines in their spectrum. According to this classification, our Sun is also part of population 1. In population 2, the brightest stars are red giants that are far advanced in their evolution. There are hardly any hot young stars here and almost no interstellar matter. Star formation is no longer taking place. These stars can be identified by their low metallicity, as they contain less heavy elements. Most of them are older than 6 billion years and are often found in globular clusters, in the galactic halo and in the core of the galaxy. The classification system used today is much more detailed and describes 5 different populations. Stars of extreme population 1 are very young, less than 100 million years old, and they can be found in spiral arms, star formation regions, nebulae, open star clusters and star associations. The intermediate population 1 includes stars that are somewhat older but otherwise have similar properties to those of the extreme population 1. According to the currently valid definition, our Sun is also an intermediate population 1 star. The stars of the disk population have an average age. This is the largest group and includes most of the galactic disk and the galactic center. The intermediate population 2 is a smaller subgroup that predominates mainly in the central region. It consists of old red stars. And finally, the halo population consists of very old stars more than 6 billion years old. These are mainly found in globular clusters. We had already learned in an earlier video that the space between the stars is huge and that our galaxy therefore actually consists mostly of empty space. Using the example of our Sun and the nearest star, Alpha Centauri, which is about 4.2 light-years away, we had seen that there is so much space between these two stars that all hundreds of billions of stars in our galaxy could fit into this space, and there would still be millions of miles between them. Nevertheless, the space between the stars is not completely empty. Within the spiral arms, it is filled by huge clouds of gas and dust, which either block the light of the stars behind them as dark clouds, or become directly visible as so-called emission and reflection nebulae. These also include the so-called molecular clouds, which have been found to be the birthplaces of new stars. Interstellar matter consists mainly of neutral and ionized hydrogen gas, some helium, very few heavier elements, and dust. However, you should not compare this dust with the dust in your home. The interstellar dust particles have an average diameter of about 0.3 micrometers and are therefore much smaller than the dust particles we know from everyday life. Nevertheless, their density can be so great, especially in the cool dark clouds, that all the light from the stars behind them is swallowed up. These clouds then appear as dark and seemingly empty areas in the plane of the Milky Way. The distribution of gas in the galaxy is determined by measurements of the 21 centimeters hydrogen line. This 1420 MHz radiation is produced by the transition between two levels in the ground state of the hydrogen atom. Due to the quantum properties of the radiation, hydrogen absorbs the same wavelength in the lower level that it emits in the excited upper state. This means that neutral hydrogen and cool dust are mainly located in the galactic plane. The radiation from the hydrogen can penetrate the dust clouds more easily than the visible starlight. This gives us a richer mapping of the hydrogen than of the stars themselves. The birthplaces of the stars, the gas nebulae and molecular clouds, are made of ionized hydrogen and dust. Most of these objects are emission nebulae as they are luminous. The interstellar gas is excited by radiation from nearby hot stars. In some cases this happens through shock waves, but mostly through ionization, recombination or excitation states. This means that an electron bound to an atom is raised to a higher electron shell, meaning to a higher energy level, by a photon of a specific energy. After a certain time, however, the electron jumps back to a lower shell and emits the difference in energy between the two shells as a photon of a characteristic wavelength. Accumulations of thin gas, mixed with dust particles, are occasionally found between the spiral arms. If stars are located in or in the close proximity of a nebula, gas and dust become visible, either by simply reflecting the light or by scattering the radiation from the stars. If no stars are present, the nebula remains dark and only indicates its existence by shading the light of the stars behind it. When a large interstellar cloud of molecules and dust condenses into stars, the result of star formation is an irregular accumulation of stars, called an open star cluster. The center of mass of the galaxy, the fulcrum of all stars, star clusters, gas nebulae and dust clouds, is located in the constellation of Sagittarius, where the visible band of the Milky Way appears at its widest and densest. Unfortunately, there are dust clouds along the plane of the galaxy, absorbing the light of the objects behind it, and the core is obscured by one of the densest dust clusters of all. Therefore, observing the core in visible light is not possible, due to the absorption by the dust in the galactic plane. Observations are only possible using long-wave radiation, in the infrared wavelength range and with radio waves, as well as in the hard X-ray and gamma range. In 1999, the X-ray satellite Rosat discovered a hot gas cloud above the galactic plane. Later observations even confirmed two such gas clouds, both in visible and other wavelengths, especially in visible light. In 2010, the Fermi Gamma Ray Telescope determined that these clouds were part of two hot gas bubbles, flowing out of the center, vertically to the plane of the galaxy. They are each 27,000 light-years long. The hydrogen gas the clouds consist of shows temperatures of several million Kelvin, therefore emitting both X-rays and gamma rays. It was previously unclear when and how these bubbles formed. In 2017, a trick was used to study them. The Hubble Space Telescope analyzed the light from 47 distant quasars, which pass through the gas of the Fermi bubbles. During the light transit, specific elements, temperatures and currents inside the bubbles left distinctive signatures in the quasar's spectrum. From this information, it has been possible to determine more precisely when this enormous amount of gas was ejected. It became apparent that the bubbles are not the result of a sustained outgassing, but must have formed in a single violent and abrupt event that could have taken place around 6 to 9 million years ago. This indicates that the core of the galaxy was once much more active than it is today. 3 years later, Fermi identified the gamma-ray source as two huge bundled jets, originating directly from the center of the Milky Way. They are about 25,000 light-years long and inclined at an angle of 15 degrees to the galactic plane. Strong radiation from the center of the galaxy has been measured for more than 90 years. In 1932, physicist and radio engineer Karl Jansky discovered this radio source purely by chance, as the strong signal coming from the constellation of Sagittarius regularly interfered with his transatlantic radio links. Later astronomers called this radio source Sagittarius A. This image from the Spitzer Space Telescope shows Sagittarius A and a massive cluster of stars surrounding the galactic center. Spitzer, which operated exclusively in infrared, has provided many spectacular views of the core of the Milky Way. Infrared astronomy allows us to see through the dust clouds, which obscure our view in the visible spectral range. The long wavelength of infrared waves allows them to turn around the dust particles. We are familiar with this from thermal imaging or night vision cameras, which also work in the infrared range and can even be used to see through heavy fog. Spitzer's images show hundreds of thousands of stars, clustered together in a close space, with dark dust clouds, bright gas masses and filigree extensions in between. This segment is 890 light-years long and 640 light-years wide. The infrared image consists of more than 2,000 individual images from Spitzer, which were combined with images from the Hubble Space Telescope. It covers 300 by 115 light-years with such a high resolution that structures only 20 times the size of our solar system can be seen. Later, images from 3 space telescopes were combined: Hubble in visible light, Spitzer in infrared, and Chandra in the X-ray range. Here, too, Sagittarius A can be recognized as a bright spot. More precise radio observations resolved this structure into various radio sources of different nature. These images are not optical or infrared photos, but radio maps of different resolutions, which were created using the radio telescopes of the Very Large Array in New Mexico. It can be seen that the central object is surrounded by a ring of colder molecular interstellar matter. Another nearby radio source is Sagittarius A East, which is a non-thermal source with a shell-like structure, probably the remnant of an ancient supernova. Non-thermal radiation, also known as synchrotron radiation, is emitted by electrons in magnetic fields. Thermal radiation, on the other hand, is produced when electrons move freely in space. This happens in a so-called plasma. Such a thermal radio source is Sagittarius A West. It consists of ionized gas. Embedded is another, but very compact and bright radio source, called Sagittarius A star. This very small but intense source is identical to the origin of the radio emission discovered by Jansky in 1932. But the special thing is, unlike all other objects in this picture, this one is completely stationary. It does not move from its spot. Obviously, Sagittarius A star is the actual core of the galaxy. Zooming in on the inner region of Sagittarius A, at higher radio resolution, reveals a surprise. It becomes apparent that Sagittarius A East consists of conspicuous narrow filaments, which are generated by strong magnetic fields and appear to be connected to the neighboring radio source Sagittarius A West. This also explains the strong non-thermal synchrotron radiation of Sagittarius A East. If we take a closer look at Sagittarius A West, another surprise is in store for us. Sagittarius A West is an almost spiral-shaped structure of ionized gas, with a diameter of about 6.5 light-years. Astronomers used to think that this mini spiral was a rotating jet, emanating from an explosion in the galactic center. More precise measurements show that the gas is part of a ring, while the jets consist of heated matter. The strong radio source Sagittarius A star is located exactly in its center. Already when these structures were discovered at the end of the 1980s, it was clear that it had to be a supermassive black hole of more than 4 million solar masses, located right in the core of our galaxy. A black hole is an object whose gravity is so strong that no matter or light can escape from this area. According to the general theory of relativity, a sufficiently compact mass warps spacetime to such an extent that a black hole is created. There are two main types of black holes: stellar black holes, which are created by the collapse of particularly massive stars, and so-called supermassive black holes, which are thought to exist in the cores of most galaxies. Gravity of a black hole is so strong that even light or other electromagnetic beams cannot escape. Consequently, these objects can never be observed directly. Their existence has been proven using indirect methods. The enormous radio and X-ray radiation measured from Sagittarius A star does not come directly from the black hole itself, but from its very hot and energetic surroundings, the so-called accretion disk. The black hole attracts gas and matter, which accumulates in the accretion disk and heats up to extreme temperatures, many hundreds of millions Kelvin. The high-energy radiation is emitted in the process. The Chandra X-ray telescope has repeatedly observed radiation bursts, known as flares, in close proximity to Sagittarius A star. It seems that a huge ring-shaped cloud of gas is orbiting around the black hole and becoming heavier and heavier in the process. As soon as a critical mass is exceeded, this cloud collapses and crashes into the core. This creates an outburst in the X-ray range. In 2019, Sagittarius A star even flared brightly in the infrared spectral range for 2.5 hours. The intensity of the outburst exceeded the typical radiation from this region by more than 100 times. Since then, the galactic core has not come to rest, and astronomers have repeatedly recorded further bursts of radiation. The most likely cause of the unusual activity is the infall of matter from extended gas clouds onto the black hole. It is assumed that the strongest flares are additionally intensified by magnetic interactions in the very hot gas surrounding the central object. With the help of special techniques, it was finally possible to obtain very high-resolution infrared images of the galactic center and to look deep into the radio source Sagittarius A star. What previously looked rather lumpy resolved into individual stars. This region has a diameter of only about 50 light days or 1.3 trillion kilometers. Even within a radius of about 500 billion kilometers around the central region, there are many young hot stars. The stars in the central cluster are so close together that special observation techniques, such as adaptive optics, were required to increase the resolution of the very large telescope of the European Southern Observatory in Chile. Adaptive optics is a technique for improving the performance of ground-based optical telescopes by reducing or compensating air turbulence, usually by moving or deforming the mirror surfaces. This made it possible to study individual stars and their orbits around the galactic core with unprecedented precision. As a reminder, these stars are more than 26,000 light-years away from us. Since 1995, the research team around Reinhard Genzel of the Max Planck Institute for Extraterrestrial Physics has been using the VLT to observe a star, called S2. In 2002, this star approached the central object to within 17 light hours or around 18 billion kilometers. During their observations, the researchers were able to detect a sudden turnaround of the star, which has a mass of 15 solar masses. Since then, a complete orbit of S2 has been observed, for which it takes a little more than 15 years. Due to the small distance between S2 and the enormous mass of the black hole, the orbital speed of S2 is very high. Its speed is up to 7,600 kilometers per second. That is around 27 million kilometers per hour, and it corresponds to about 2.5% of the speed of light. Surprisingly, the orbit of S2 is fairly stable. It would not be torn apart by tidal forces until S2 approaches the black hole at around 300 million kilometers. Until today, many other stars have been discovered in the area around Sagittarius A star, some of which come significantly closer to the black hole than S2, and even have much higher orbital speeds. Due to the rapid speed of these stars, their motion can only be interpreted as orbits around a supermassive black hole. The current record holder is S62. This star approaches the black hole to a distance of 2.4 billion kilometers, which is less than the average distance between Uranus and the Sun. S62 rotates around Sagittarius A star in less than 10 years and in a highly deformed orbit. It passed the closest point at a speed equivalent to about 10% of the speed of light. In other words, at almost 30,000 kilometers per second. This makes S62 the fastest object ever observed. Although astronomers are unable to see the black hole directly, its mass can now be determined in a similar way to the mass of the Sun by observing the parameters of the orbiting planets. Using this method, the mass of the black hole could be determined to be almost exactly 4.3 million solar masses. The size of the black hole in our galaxy's core is enormous. Assuming that it is a rotating black hole, as many things indicate, its radius is probably around 10 million kilometers, which corresponds to about 15 times the radius of the Sun, or 1,700 times the radius of our Earth. Today it is accepted that every galaxy has a supermassive black hole in its core. Some of them, such as the one in the giant galaxy M87, are much larger. It probably has more than 6 billion solar masses. In some giant galaxies and quasars, the black holes may even have reached up to 20 billion solar masses. It is still unclear how these gigantic black holes were formed or how they came to be in the cores of galaxies. They probably formed very early on in the evolution of the universe. We will hear more about them when we talk about active galaxies in the next video. The significance of the discoveries around the galactic center were recognized in 2020 with the Nobel Prize in Physics, including for Reinhard Genzel, the director of the Max Planck Institute for Extraterrestrial Physics. Since then, research has focused on using the galactic core as a laboratory in order to test the general theory of relativity in the very strong gravitational field near the black hole, and to determine its properties. For example, the orbits of the stars in the central S cluster are being measured with increasing precision. The MPI researchers used the gravity near-infrared interferometer to closely observe infrared light from the region around the black hole and search for flares. These flares still occur very frequently, once or twice a day, and they are so bright that the movement of the surrounding gas can be tracked. Flares observed in 2018, 2021 and 2022 were analyzed so that the origin of the outburst and the polarization of the radiation could be measured simultaneously. The data allowed the team to determine the mass of the black hole with greater accuracy than before, at 4.297 million solar masses, with a deviation of only 12,000 solar masses. This was another significant and independent confirmation of the earlier measurements. The new data also showed that this mass must be limited to the radius of the flares of about 9 gravitational radii, which is smaller than the orbital radius of the planet Venus around the Sun. This points to a single giant black hole at the core of the Milky Way. But there was still no image of the black hole's immediate surroundings. If it's really there, then at some point we should be able to discover the accretion disk where the high-energy radiation comes from. So the next goal was to obtain a direct image of the innermost region of Sagittarius A star. Observations were made for a long time and everything was tried, but the telescopes and techniques used until then were not sufficient for this task. In 2022, after years of research, a team of scientists from the Event Horizon Telescope Network finally succeeded in imaging the accretion disk of Sagittarius A star directly. The EHT is a global consortium of several observatories, 80 institutes, and more than 300 scientists. The method used is called Very Long Baseline Interferometry. Radio telescopes all over the world are interconnected to operate as a single gigantic telescope. It allows radio measurements with enormous resolution. Nevertheless, data had to be collected and analyzed for many years before the results could be published. The finally published radio image shows a ring consisting of glowing gas. It surrounds a dark central region, which the scientists called the shadow. Due to gravity, the light from the ring is strongly bent and diffracted. This ring is actually the predicted gas ring, in which the radiation outbursts take place. 3 years earlier, the EHT team had already published images of the supermassive black hole in the galaxy M87. At that time, images of Sagittarius A star, taken with the global millimeter very long baseline interferometry array, which is another worldwide network of radio telescopes, showed only a luminous disk, but not yet a shadow as in M87. It was therefore hoped that the resolution would be higher at a wavelength of 1.3 millimeters, as the effect of interstellar scattering is lower here and can be corrected. The resolution is so high that we are moving in the micro-arcsecond range here. An arcsecond is known to be the 1,800th part of a degree. A micro-arcsecond is in turn the millionth part of an arcsecond. The angular diameter of the gas ring around Sagittarius A star is about 52 micro-arcseconds. It should be emphasized, however, that this image still does not show the black hole and the shadow is not identical to the black hole itself. The so-called event horizon, the surface of the black hole, should have a much smaller angular diameter. Presumably a maximum of 10 micro-arcseconds. Possibly even less. So, our black hole has indeed a dynamic and turbulent accretion disk. It rotates quickly, the innermost stable orbit has a period of less than 30 minutes, and the rotation axis is inclined about 30 degrees to the line of sight. The accretion disk is therefore almost perpendicular to our line of sight, as already suspected before. The angular momentum did not yet result from the EHT observations made in 2017. This will probably take several more years to analyze. It was also surprising that no jet was visible, as was the case in M87, especially as the black hole in our Milky Way is currently very active and dynamic, probably because the angular momentum is too small. However, if there was one, the jet should be directed exactly towards the Earth, due to the nearly vertical line of sight. Lastly, the EHT project observed Sagittarius A star in polarized light and recorded its swirling magnetic fields, which is strikingly reminiscent of an older image from the EHT showing the supermassive black hole M87. The new picture shows a clear polarization pattern in the particles orbiting the black hole, which means that they are influenced by strong magnetic fields that wrap around the limb of Sagittarius A star. Strong and organized magnetic fields are thought to be common to all black holes. Since the magnetic fields of M87 cause strong jets, Sagittarius A star might have its own, but weaker jet. Since both black holes have similar magnetic field structures despite their immense difference in size and mass, EHT scientists now suspect that all supermassive black holes could have such magnetic structures. So it remains exciting, as we keep waiting for further insights into the heart of our galaxy. Maybe the large amount of petabytes of data, not yet analyzed by the EHT team, will reveal further surprises. Thank you for your interest. In the next video of our series, we will look at the surroundings of our galaxy, and the other members of our galaxy cluster, the local group. And we will learn that our Milky Way is a voracious monster that has already consumed some small galaxies in the past. Please leave a like and a subscription. See you soon and goodbye.